Hi, and welcome to the next section in our gradient boosting chapter, which is the second subsection on gradient boosting with trees. So this is more of a deep dive here. So we'll discuss that and how terminal coefficients can be fitted in a loss optimal way if you use trees together with gradient boosting. And I will at least discuss very briefly how this works for multiclass trees and gradient boosting. So first of all, we've discussed this before. We can write down trees as an additive model, as you can see here. So as an additive model across the partitioning that's induced by our leaf node regions times some height constant C. And the gradient boosting model is now still additive in these regions, which is really a super simple conclusion of or implication of that the gradient boosting model itself is additive in its base learners here. So I've written this in a recursive manner where we have here the model that was fitted until now, and then we have adding in the nth component, and this nth component you can again write down as an additive model over the regions of the tree. So far so simple, and if you wanted to, we did that also when we discussed the interaction depth of the gradient boosting model. You can now kind of write this as an additive model across regions for the whole model. Now, one nice thing because of this additive structure is that you can do some kind of post-hoc adaptation, loss optimal adaptation of these height coefficients here. So what we can do is that after the tree has been fitted in an individual boosting iteration against the vector of pseudo-residuals, we can now only keep the tree structure but change the height of these terminal regions here in a loss optimal manner. So remember that these guys are not really chosen in a completely loss optimal manner when we fit it against the vector of pseudo-residuals with L2 loss. So there's kind of an approximation going on here when we do that. So there might be room of improvement for these guys here. So what we will now do is we will consider this. You can kind of see that this function here, because of its additive structure, is now kind of separable in these components here. So we can kind of adapt the function individually for C1, individually for C2, C3, and so on. So for each of these heights, and that will not influence anything. There is no interaction going on with these C's among them. So we can now simply write down our model as it is, and the risk of our model as it is, but make one constant here for one terminal region flexible, variable, and fit that, for example, through a line search. Or maybe through some, gradient step, depending on how differentiable our loss function here is. There's also an alternative approach we can also try to do that directly to fit a loss optimal tree. So we can also take a look at here how this risk function can be written for the data in a node. When we kind of add in only the data points in that node here. And remember that our nodes form a partition of our space, right? So each data point is in exactly one of these leaf nodes. And what we can now also do is that while we are constructing the tree, we can already use that risk function here with that given loss, the loss that is handed down to boosting. We can push it further down into the tree and then fit our tree and find the optimal split points and the optimal C values directly in the tree fitting algorithm. That of course implies that we have a flexible tree algorithm in front of us that's formulated with respect to arbitrary loss functions, and that really uses risk minimization as a principle to find the tree that's possible. Not all software is written in that manner, unfortunately. So sometimes we have to resort to this here, but a direct approach is also possible. Now, for the last 2 to 3 slides, I also want to mention what happens for gradient boosting with multi-class problems with trees. So this is actually a bit more complicated as regarding this optimal adaptation of the terminal heights. So again, what we do is we fit one discriminant function per class. Maybe let's directly go to the pseudocode here. So we have this lengthy pseudocode now for the gradient boosting algorithm. Everything in here is, we've seen that before. So we have some initialization going on. So we can, for example, initialize with 0, or we can probably also do something better by initializing with the a priori probabilities for our respective classes. And we have the boosting loop going on here for m iterations. And what happens, and on the inside, we will now fit one discriminant function. So, such a function fk or pi k. So pi would be for posterior probabilities. So I guess we're fitting these guys here, these fk's, these scoring functions. We will fit one discriminant function per class. So this is why we have this extra loop going on here. We have also discussed this before. Now, if we want to transform these G scoring functions into posterior probabilities, we can do that through the softmax transformation. This is what happens here. This is also not super surprising or complicated or new. Here we compute our vector of pseudo-residuals. So that is the 0, 1 encoded vector for the current class that we're currently looking at. And here we we compute now the pseudo-residual by subtracting pi k. Now we fit against this vector of pseudo-residuals, and everything is as before. We've discussed this before in a previous section on how to handle multi-class problems with gradient boosting. What is more complicated is how we would proceed in order to do this post-hoc adaptation of these C values here. And for that, there's unfortunately really no closed form solution. The regions corresponding to the different class trees, they overlap. So that makes everything more complicated. And what is usually done is that we approximate the solution with a single Newton-Raphson step. Actually, we're using their further simplification by assuming that this the Hessian only has diagonal structure. I've left out a lot of details here, so if you're interested in that, take a look at that paper here. And I'm mainly stating the result, which is this somewhat complicated formula here. Maybe I'll add a deep dive as a further section later on where we just look at how this formula is derived. So I'll leave it at that here and stop the video